Okay. So, I repeat, an analog signal band limited, which is a band limited function or band limited signal, that is, if you take the analog Fourier transform, it is limited from minus omega h to omega h for highest frequency. So, h, okay, actually the magnitude is limited from minus omega h to omega h, okay, that is 0 outside this zone, and it is sampled now to generate a sequence x n, where x n is nothing but x a the n into t. N into t is a time point. At that point, whatever is the value of the analog function, that I am calling n sample of the sequence. That sequence, and I am sampling following Nyquist condition, that is, I am sampling at an analog sampling rate of 2 pi by t, t is the period, sampling period, that is greater than equal to twice the band limiting frequency. Then you have seen that the sequence which I obtained by sampling this analog function at that rate, that is at period capital T, is DTFT will take this shape, where from minus pi to pi whatever you see, that is a replica of original analog Fourier transform. Only thing is, it was a function of capital omega, it is a function of small omega, and a multiplication by 1 by capital T of this took place, because that was the formula 1 by T times this. Okay. Otherwise, shape wise it is same. Therefore, it leads to an interesting question, that what is this DTFT? And again, since capital omega is greater than equal to 2 omega h, half sampling frequency omega base by 2 is greater than equal to capital omega h, half sampling frequency maps to pi, capital omega h maps to small omega h, so pi is greater than this. So, whenever there is no aliasing, half sampling frequency is greater than equal to the band limiting frequency, or in digital domain pi is greater than equal to small omega h. Small omega h comes from capital omega h. This is the situation. So, we are assuming no aliasing case, because Nyquist condition was satisfied. Then what is this DTFT? We know DTFT for any small omega on this axis of your choice is okay. This is the DTFT. But DTFT, if I restrict small omega from minus pi to pi, that is, I plot only this function, then this looks very much like this. There is no right half, there is no left half, only this much, otherwise 0. Okay. So, you see capital X e omega, if I take from omega from this point to this point, sometimes I can go up to this fully. Okay. That is, if 2 pi by t is equal to 2 omega h, then half sampling frequency will be equal to omega h, pi will be equal to omega, small omega h. So, we will start directly here. In some cases, there will be gap. That is why, to be most general, I take from minus pi to pi. Okay. I take the DTFT. That is, I do not look at frequency points omega to the right or to the left, I see only here. Okay, this function, I look at it. And then here, then here small omega, wherever there is small omega, I represent it, write it by capital omega t. Okay, so, it will become a function of capital omega, and then I multiply it by capital T, because this was obtained by dividing by T. So, this can be obtained in one band by multiplying by T. So, that means T times capital X e to the power j DTFT is not analog Fourier transform, is DTFT, but small omega replaced by capital omega t, radian per second into second, that is, so it is radian. Okay, this is a DTFT. This function will be identical to this, because I am multiplying by capital T, and replacing small omega by capital omega. So, I should get back the original one, okay, from here to here. Not, don't include these side ones, because they are not present there. That is why first thing I am doing is restricting omega in the range minus pi to pi, and then doing the reverse frequency mapping. For small omega I am going to capital omega in the DTF2 itself, multiplying by capital T. So, resulting thing is a function of capital omega, that is same as this, which follows from here. Okay. Therefore, now look at this original function x a t. What is x a t? Is the inverse analog Fourier transform of this but this guy is band limited. It is from minus omega h to omega h. All right. Here first, this part I replace by this. We have already seen that they are same. So, T sorry, this is omega, I am very sorry, this is omega. I am not even looking into this omega, it is inverse Fourier transform. Okay. All right. But there is no point in taking the integral from minus infinity to infinity, because this function is 0 outside this range. Okay. So, I take it from just a minute. I can take it from minus omega h to omega h, but to general suppose I take it from here to here, because sometimes this can coincide with this. Outside this is 0. So, no point in carrying on the integration. This capital T can come out, this is this. But this is DTFT at this D. So, I can replace it now by the DTFT expression. J this much analog digital frequency omega t into n, this into e to the power j omega t d omega. All right. Now, there is a double summation. So, you know very well what the next step is, interchanging the two summations. All right. So, next step T by 2 pi, this inner summation goes out, x of n, it does not depend on omega, inner summation is with respect to capital omega, this does not depend on, so this omega, so this can come out as common. Okay, and I am left with this inside, e to the power j capital omega t minus n t d omega. All right. So, this we integrate with respect to omega. that is what we get. This integral with respect to omega. So, j t minus n t will come below, and it will be same as j omega t minus n t and omega s by 2 . Okay. Then what happens? E to the power j theta minus e to the power minus j theta. So, it is twice j sin theta. So, t by 2 pi twice j sin whatever I am writing that here j t minus n t. Of course, there is a summation x n that I am forgetting. There is a summation, this part I am okay. So, this I write again. Maybe I write on a fresh page. This page does not have much space. So, this integral t by 2 pi summation x of n and then this twice j sin this omega was omega s by 2 and then minus omega s by 2. So, it is omega s by 2 into this quantity. If you want, you can see, look at that thing, e to the power j omega t minus n t remains, j t minus n t here, replace omega by omega s by 2 and then again minus omega s by 2, that minus this. So, it will be twice j sin omega s by 2 into t minus n t divided by this. So, twice j sin omega s by 2 into t minus n t divided by that j t minus n t. So, j and j cancels, 2 cancels, t by pi, you can bring the t by pi here below this as pi by t and t minus n t, this x n sin omega by s by 2, omega s by 2, what was omega s? 2 pi by t. Okay. So, what is omega s by 2? It is pi by t. So, if I bring pi by t here, pi by t into t minus n t. So, actually it is a sinc function, okay. Delayed sinc. It is sinc of this, if we call it x, sin x by x. So, sinc so, you see this is a very interesting, very important result, that we started with original x a t. So, if the function is band limited, and it is sampled following Nyquist theorem, then from this sequence the samples, because you are sampling, so you are getting a sample train and that forms a sequence. So, from the sample values you can get back a full original signal, analog signal, just by this summation. Okay, these are fixed functions, and when n equal to 0, so x n x 0 into just sin pi t by capital T and pi t by capital T. Then x 1 delayed version of that, x 2 delayed further delayed version of that, and they get superimposed, and by superimposition you get a function of small t which turns out to be x a t. This is the fundamental theorem in DSP, that if the function is, if I start with an analog function and it is given that is band limited then I can always sample it at more than twice the bandwidth, and all information of the envelope x a t, all information about the envelope x a t, that will be contained in the sequence in the samples, because from the samples I can recover back my x a t. Okay. So, if the function is band limited, I should sample it at more than at least equal to twice omega h or more than that, twice the band limiting frequency. Then the samples I get, which form a sequence x n, that carries all the information about the full analog signal, because using those samples I can get back by a formula like this the full analog function correctly. This formula is called Nyquist interpolation formula. We can try to explain try to understand how it looks like. Consider this function sin pi by t divided by pi by t into t. This function, how will it look like? There is small n equal to 0. After all, if it is small n equal to 1, this will be just shifted to the right by capital T. Small n minus 1, this entire thing will be shifted to the left by capital T, so on and so forth. So, I am considering n equal to 0 case. It is sin x by x. At small t equal to 0, it will be sin 0 by 0, 0 by 0 form, and then you apply the L'Hospital theorem, differentiate the numerator and denominator. You have pi by t into cosine, and here you have just pi by t. So, they cancel, and at t equal to 0, what you have? You have 1. Okay, sin pi by t into t, if you differentiate, pi by capital T comes out and you get cosine of that, and here pi by t, the two cancels. Now, if t becomes 0, this is 1. So, it goes to 1, and then small t, suppose it is capital T. So, look at the numerator. Numerator is just pure sinusoid function. Okay, numerator, if I have just numerator only, that suppose sin pi t by t, this is a pure, just numerator, this is a pure sinusoid function. Okay. At t equal to 0, it will be 0. Then at t equal to capital T, again sin pi, it will be 0, and at t by 2, it will be maximum. Okay, t by 2, it will sin pi by 2, and like this. Okay, it will be periodic. And it will go on like this. So, it will be crossing 0 at capital T, 2t, 3t, like that. But the denominator function, if you leave out the point t equal to 0, at t equal to 0, you have to apply L'Hospital, because it is 0 by 0 form. So, that is why it is not 0, it is 1. But after that, this function is periodic, but this is, if t is positive, it is growing in magnitude. So, denominator is increasing as t increases. So, this sinusoidal oscillation will get damped. So, damping. Same for the negative side, magnitude of the denominator is going up. So, it will be damped. So, t equal to capital T, in the denominator you have t t cancelling pi, but the numerator 0, and it is varying sinusoidally. So, it will come like this, and it is getting damped. So, it will not go fully up to -1, it will come back here. At 2t, it will be like this, then 3t like this, then like this. Okay. On this side also you can verify minus t, minus 2t, minus 3t, like this. This will be this function. When n equal to 1, it is t minus capital T, t minus capital T. So, the entire thing will be shifted to the right by capital T. T equal to 2, twice t, like that. Now, let us try to understand what this formula means. Nyquist formula implies take the case of x n equal to 0. So, you have the term x 0 into sin pi by this sin pi small t by capital T divided by pi small t by capital T. So, this function is to be multiplied by x small 0. So, it was 1 here. So, height will become x 0 and then it will be like this. This is t, 2t, minus 2t, 3t like that. Then consider n equal to 1. It will be x 1 sin pi by capital T, then within bracket t minus capital T divided by pi by capital T within bracket again t minus capital T. So, instead of t, it is t minus capital T, which means the entire function will be shifted to the right, moved to the right by an amount capital T, which means this and then multiplied by x 1. That means the entire same function origin will move here and it is multiplied by x 1. So, height will be x 1 say x 1, it will have 0 crossing, t to the right, further t to the right, here also like this. Then if n equal to 2, this is further shifted to the right, multiplied by x 2. So, it will be here, origin will move here, zero crossing, like this, so on and so forth. From this side also, here again you can have another one multiplied by x minus 1 going like this, okay. Now, when you superimpose all of them, you see, consider n equal to 0. At n equal to 0, everybody else going through origin, only this fellow remains as it is. So, summation will be x 0 because others are 0. Similarly, at capital T, this is going through 0, this is going through 0, this is going through, only this fellow remains, his value is x 1. So, at capital T, value remains x 1, at 2t, value remains x 2, at minus t, value remains x minus 1. At intermediate points, they get added, and that is how this function is formed. Function I know at x at n equal to 0, resulting function, analog function has sample how much? Just a minute. At n equal to 0, analog function has value x a 0, which is same as x 0, 0 is 3. So, that will come up. Then at n equal to t, you have got x a n x a t, which is same as x 1. So, this will come up. This x 1 is nothing but in terms of analog x a t. So, x a t coming up, x a 0 coming up, x a 2 t coming up, and intermediate points they all get added because they are overlapping, they are get added, and the envelope gets formed. This is the meaning of that summation. But this is again a fundamental thing. It means that if you have got an analog function x a t and that is band limited, then you don't need, you can sample it at twice or more than twice the band limiting frequency. You get a sequence of samples, train of samples, which forms a sequence. Using those samples, you can get back the original envelope by a interpolation formula, which is called Nyquist interpolation formula. Okay, this interpolation formula. In fact, giving these samples, you are giving only these samples, you can now construct the envelope and you can get the value at any arbitrary point, any arbitrary maybe t by some k, okay, that kind of thing. So, this interpolation is that way very useful, you can have fractional sampling point, the value there can be obtained in terms of these samples. Okay. This is a very interesting topic in DSP. So, that is all for today's class. In the next class, I will consider a special kind of linear time invariant systems called rational system. Thank you very much.